Does your computer?
Why would you do that?
Why does your computer do that?
Why did you make it do that?
I'm expecting like a little bit of steam to come out of the side.
Wait, what button did I press? Okay.
Oh, yeah, okay. That looks fuzzy. Hi class, what's up?
Hello.
Instead of finishing big RSA, one of my friends, not my friend, one of my friend's friends was like, hey Calvin, have you played the new Monster Hunter? I've played 26 hours of Monster Hunter since I woke up on Saturday. It is the only thing I have done. You know what I was doing before that? While it was downloading, I got Bloodborne to work on PC. I have completely fallen back into my old ways. I am currently an undergraduate. You think you're the people that play video games instead of doing your homework? That's me now. Anyways, I did not finish Big RSA this weekend. That's what I was supposed to do instead. Would that have actually been more interesting? Yes. For those of you that don't know, Monster Hunter Wilds does not, to my knowledge, contain my favorite monster in the Monster Hunter franchise, Rabadon, who is my favorite monster in the world. I did not know that until I killed every single monster in Monster Hunter Wilds, which took me 26 hours. I'm a bit upset and a bit put off by this, right? I'm up in my feels. Any of you have ever felt a feeling before? Anyways, I also started watching anime, so now I feel my own feels all the time. I currently listen to emo music, watch anime, and play video games. Nier Automata version 1.1a, which is not really anime, sorry. Besides Nosferatu 1922, it is the only screen media I watch voluntarily. So, anyways, I owe you all an apology. The instructional quality is correspondingly lower because my personality came back. It happens to the best of us. I thought I would be able to get through this term, and in fact, Big RSA is way funner than Monster Hunter Wilds. It's also a lot harder. I was like, I need something easy to do. So I started playing Souls-like video games. Anyways, I have released the Big RSA assignment. I think I have to issue one correction. I am pretty sure, I thought about this on the drive down here, that if you have a 496-bit integer type, that the largest key size you can use is a 2048 key, because you have to do modular exponentiation with a key size of 2048. Which means you have to multiply two numbers by each other, which can get up to 496 bits in size if they're 2048 input types, right? Which means to implement modular exponentiation on a 4096-bit key, well, you actually have to have an 8196-bit precision integer type. Huh? 8196, right? 40, no, 90, oh, did you say 92? Yeah, I misheard you, yes, 92, sorry. What did I think you said? My brain's not working. It only understands Japanese subtitles. Amen. Okay.
Subtitles are in Japanese.
Yeah, I try and not acknowledge the English language while I'm in my free time, which is a problem because I barely understand English, much less other languages. The only language I voluntarily read and write in is C89. Dang it, almost. I almost landed the joke. Oh, it was so close, right? I was locked in, and at the last minute, a gust of wind blew my plane over, much like planes in the United States. Okay, never say I don't follow current events.
I didn't dream I was in a plane crash.
What?
I didn't dream I was in a plane crash last night.
Do you think it, should we psychoanalyze it?
No.
Okay, so I'm thinking you were probably working on Big RSA, right?
No.
Well, that's what I was working on. Okay. Big RSA is due the 31st of March. You have 1 month. I think we'll need the whole month. I don't have it working yet, and I don't really have a work ethic, so maybe that's the problem. Have any of you, how far is the furthest person in this class? Does anyone have big prime generation done? Do you have regular prime generation done?
Yes.
Okay. I'm worried that 6K plus 1 will just straight up stop working somewhere around 200 bits. Like, you will run it and you will never know if it's going to find a prime or not. Do you know? What's the biggest prime you've ever generated?
Like 2,000 bits.
Okay, how long did it take?
Well, I was using an inefficient method.
How long did it take? We're not using an efficient method, right? We
Like
wrote
a
our own
minute.
division. Huh?
Like a minute.
Okay, that seems reasonable.
I got
Something
like
like that.
3 lines of digits in base 10 using Linux checking and just adding 2.
Okay, so 3 lines of digits in base 10, right? So we're going to assume that your terminal width was 80 characters, right? So that's 240 characters base 10. In binary, we would have roughly 3 binary digits per 10's digit character. So that's 240 times 3, which is roughly an 800 digit prime. Okay, and it took you how long?
It took like, it was like, I wrote it in Rust and it was like 2 minutes per prime.
Ooh, okay. So if we had 2 minutes at an 800 digit prime, right? How much longer does it take to generate an 801 digit prime? Well, it takes twice as long, right? So we have to get up to just a 1,000 digit prime. We have a problem, right? Because it's going to take 2 to the 200 times longer than 2 minutes. Anyways, I think the way out of this particular pickle is I'm going to look up OpenSSL and SSH keygen, which are the 2 reference solutions. And one of them lets you produce 512-bit keys, and the other one lets you produce 1024-bit keys. And it's possible that mere mortals like us can produce those keys before the sun goes out. One thing to keep in mind is if you're using a big division you wrote yourself, which I will be, that big division is probably real slow and probably super bad and really inefficient because we don't actually know how to do things well. We know how to do them at all, right? And we get some credit for that, right? Doing things at all is the first step to doing them well. Is that a metaphor? No, that's just the literal truth, right? Yeah, okay. Anyways, work on big RSA. I think if we all put our heads together, we might get more than one solution out of this class. And I think you should all work together. Okay, how's everyone doing on RSA and C? That's imminently possible, right? Okay. Yeah, I think we'll all successfully do that. Any questions? You look happy. You happy?
This is a fear grimace.
That's a fear grimace? Can we ever truly be happy if we're not also afraid?
Yes.
Yeah.
Yeah.
Okay, I didn't know that. I've never tried, right? I've been afraid my whole life. Afraid of, being my true self. Afraid of turning off the C89 compiler flag on GCC. These things keep me up at night. I don't have dreams about frame crashes. I have dreams of compiling in C99, right? Okay, so, there's a midterm next week, right? So here, I thought we should talk about it, right? Because that's the first step to feeling really good about things. I want to let you all know that the MSCS students, they don't have to do the midterm. And they successfully did this by being so far behind, they will not finish the class on time. So you're being punished for being successful, bully for you, right? Good job. Can I hear it for you? So in real life, when you do a good job, you get rewarded with more and harder work that's correspondingly more stressful, and so we're going to preserve that in this classroom. The midterm, I will give you the sample midterm, and to me it will be staggeringly, unbelievably obvious what the actual midterm will be as soon as you see the sample midterm. And I don't know if it'll be obvious to you, so we'll find out, right? The sample midterm is I was going to intend to give it next Tuesday. I think I have found a task that you can implement in C in 90 minutes and turn in your code. I have no idea how to implement that logistically. My line of thinking was we just do a Google Classroom angle, or no, GitHub Classroom? GitHub Classroom? I'll write up 2 assignment descriptions. One of them will be for the practice, one of them will be for the actual. And that'll be that. It's going to be based on the idea of encoding information in bits. That's what we've been doing this term. I'm not going to make you do any number theory. I think the number theory is good for you to hear about, but I'm not asking you to do independently generate new number theoretic ideas, right? But I am going to ask you to follow algorithms.
Did you say next Tuesday when we give the sample midterm?
Yes.
Is that like you assign the assignment and then do it on your own time, you do it in class? Or you do it in class?
That is a good question, and I want to loop back to that.
Okay.
On Thursday, we have the actual midterm. Now, generally speaking, because I think like other classes at this university, they give out paper midterms and like collect them and proctor them and everything. So traditionally, we would conduct the midterm in class. But we don't have to do that. Do you all want me to come here and administer an in-person midterm? And I can do that for both the practice and for the actual, or for one or for both. What do you want?
You do like an A/B.
Yeah, okay, so who wants to be here in person next Tuesday for the practice? Okay, that's enough of you, will come down. The alternative is I send out an email.
We don't have class.
No, we still have class, we're having it remotely. Because you might want to do the testing in like some other environment or something. Yeah, so either I can be in this room, and I think if I come down here, I'll expect you all to be here. That seems reasonable, right? I was going to let you do the practice in groups, so you can talk to each other. So that would be another reason to be together for that. And then the actual midterm, I wasn't going to like enforce that you can't talk to each other or anything. I'm just assuming that it would be weird to not do it on your own to see how you're doing in this class. But I am somewhat relying on your intrinsic motivation. So then I was going to do the exact same thing on Thursday. And then once again on Thursday, you might want to have, do you like live in dorms or something? Like where do you do homework usually? The library?
Upstairs.
Upstairs? Okay, so you would be in Ford anyways. Okay, so why don't we just do them both as normal classes, and I will like look at you while you're typing. Okay. Yes.
Would there, I know I was one of the people raised my hand to do it in class, but for people who didn't want that, would there be an option to do that digitally?
I'm not going to take attendance. Which I never do, right? Around this time of the year, my commitment to my core beliefs in grades being made up and not mattering is tested by the presence of all of the other faculty doing midterms and getting like really agitated about what the class averages are and stuff, right? I maintain that my analysis of what grades do and accomplish and how I'm using them in this class is consistent with the learning objectives of this class. That said, it is fundamentally weird to be this far outside of the norms, right? So I would like you to treat the midterm as you would as if it decided your future without being as stressed about it as you would be if it decided your future, right? So I would like you to take it seriously, make an effort to do a good job so that you can learn the most, and then not have like elevated blood pressure like I always had on my midterms. I don't know if you all had this experience. I took exactly 17 times 3 math midterms in undergrad, or 2 midterms each and a final for 17 classes. And I did not sleep the night before a single one of them, which is a large number of lost hours of sleep. Now, this means that I am immune to having to sleep before stressful events, right? Because I've been inoculated. I'm invincible. But I don't necessarily want that to happen to you, right? I think that might be unhealthy. I'm not 100% for sure. Here's a fun story. So I flew out to Grange to launch their MSCS program. You remember because I canceled class. I forgot to set my alarm, and I woke up at the correct time to go to the airport without my alarm going off because I'm so used to being so stressed out I can't sleep, right? It's an evolutionary adaptation to surviving capitalism. Okay. Next week, bring something you can write code on to class for both days.
Like we don't normally do that.
Well, usually I write my code on an Abacus, and I only see laptops here. Also, that one has the Windows logo on it, so I don't know that I trust that. I'd make sure I have, like, maybe NixOS on it or something before I come to class. I've been explaining to Wits that I intend to put Fedora on the next laptop they give me, and they're not really sure if that's legal or not. So I think I might just stop telling them that's what I'm going to do. Have you all heard of algorithms before?
Once or twice.
Yeah, so apparently an algorithm, and I didn't know this, an algorithm is a procedural way to solve a problem, right? So for example, I've been playing this video game called Monster Hunter Wilds, and the procedural way to solve problems in that video game is to hit them with your greatsword. We're going to use the exact same technique to do division. We're going to repeatedly hit a larger number with a smaller number until little pieces break off, and we learn something about the larger number. So we're going to begin with the notion of Euclidean division, which I believe is what invented division. It's division through repeated subtraction. Then we're going to do the Euclidean algorithm, which is the same thing. Then we're going to do the extended Euclidean algorithm, which does one additional thing. It finds out Bezour's. Does anyone know how to say that name? Bezour? So we're going to find Bezos's identity. Can I get a hail corporate? Correct. That was a test. You all passed. So we're going to figure out Bezos' identity. Did I say that correctly?
Yeah.
Bezos? Okay. My battery's running low.
You might want to plug in your PC.
I think it is plugged in. Oh, no, this thing came out.
I was just getting excited.
See, I was thinking about
Class, I was like, just come back and I was like, have you told me about this? Or yes.
Okay. Let's do some review. Do you all remember the totient function? I think we can all remember Carmichael's totient function. One of our oldest friends. We go way back, right? All the way back to whenever Carmichael was totient-ing. We apply Carmichael's totient function, which is named lambda, after the funnest and coolest letter of the Greek alphabet. That's Greek, right? And where is Greece?
That way.
It's on the Mediterranean, west of the Balkans? Is it east or west of the Balkans?
It's slightly east.
It's in between Italy and the Balkans, right?
No.
No? It's in between, the Balkans are in between Greece and Italy?
Balkans, Italy, Greece. So,
They're like a triangle?
yeah.
Oh, like they're all like friends, but they're on a daytime television show. I love triangles. One of my favorite shapes that is congruent to itself, or something like that. Okay, so we're going to calculate lambda of n, and what is n? N is the product of the two primes we generated. Remember when we were talking about prime generation way, way back at the beginning of class? Does anyone remember that? It was a long time ago. Okay. So we generate primes as part of the Rivest-Shamir-Alderman public key crypto system, also known as RSA, right? It's named after the best programming language, the antecedent of the best programming language, and the grade you're going to get in this class, RSA, right? Okay, so there's fast ways to calculate Carmichael's totient function, and I claimed that last week and I did not show you. This week I'm going to show you. It turns out the way to do that quickly is this little thing I like to call subtraction, right? We're going to do a bunch of subtractions really, really quickly using a device called a computer, okay? So this is how we implemented LCM, and actually we didn't implement this. This is least common multiple. I said, my dearest GitHub and or Gemini, I don't remember, I asked some generative AI, can you quickly write a LCM calculator? And why did I ask this, right? This is, to me, a great use of the generative AIs, which is I didn't know how the average human solved this problem. So I invented something called a transformer that predicts exactly what the most popular human would do to solve any problem, right? It picked the most likely character to come after a previous character several times in a row. And it wrote this thing. This is multiple assignment. We store the previous smaller value in A, and then we store the larger value modulo the smaller value in B. And we expect A to always be bigger than B, right? And we proceed until B goes to 0. When does B go to 0? When A is evenly divisible by B. So we're going to do a series of modulos. This does happen to be the Euclidean algorithm, but it is unlabeled. And the Euclidean algorithm finds the greatest common divisor of A and B. If this doesn't make sense to you, not to worry, I have prepared 66 slides about this. Can I hear it for order 66? Right? Okay, some of you got that right. So, right, the Empire is bad, right? We remember this? Yes, they start wars and hurt people, right? And who is good in Star Wars? The working class and the oppressed, same as real life. Okay. You may have also remembered we computed the multiplicative modular inverse of something. And what is that? That is the value such that when we multiply that number times e and take the product modulo the totient function, we get back 1. Because 1 is the multiplicative identity. We're multiplying things together to get them equal to 1 when we take a modulo. This should appear obviously inefficient to you because recall, this thing, hide lambda, is supposed to be the LCM of two things that are enormous, right? These are supposed to be 1000-bit primes, which means that this is quite likely to be 2000 bits. We don't know what the GCD will be. Probably not that big, maybe pretty big. I don't know. But we do not expect it to be that large. So we expect this thing to be roughly 2000 bits in size, perhaps, right? And if this thing is about 2000 bits in size, right, then we have to add 1 to d 2 to the 2000 times. And 2 to the 2000 is a big number. How big is it? It's really big. Yeah, it's comically huge, right? It's certainly more than the number of particles like in the galaxy, right? But maybe not the universe, something like that. Is that anyone here in Data Cosmos? How many subatomic particles are there in the universe? Do we know? It's got to be like more than 7 and less than infinity, right? Which is the exact same range that 2 to the 2000 is in, right? Did you say 80?
I think.
Oh, okay. We're in big trouble then, because our number was much larger than that. Okay. Some of you all remember modular exponentiation. Do you all remember modular exponentiation? Do you remember it?
Yes.
You remember it? No? I got 2 not 2 shakes and 1 nod.
I think a refresher would be lovely.
I think a refresher would be lovely, right? Okay, so say I've got a number, right? We'll call this number m because that's the number we're moduloing, right? And we're raising it to the power e, which is the exponent. And we're taking it modulo some value n. In this case, I didn't write this here to spell out men. Don't think that. This is message encryptor modular base n, right? I would have embedded the weather girls It's Raining Men in this slide if I'd noticed that before class, right? Okay, so what are we doing here? We have a message. The message is the bit encoding of the information we are trying to secretly transmit. This is the sensitive state secrets that Edward Snowden is telling Glenn Greenwald, for example. This is also, I'm using spoiler tags when I was discussing Monster Hunter Wilds, so that information is encrypted, right? M is the name of my favorite monster in Monster Hunter Wilds, which is Guardian Rathalos, right? So we can all understand that. E is the encryptor value. This is 65537 in virtually all cases. What is N? N is the product of the 2 primes. This is different every time. Where is it? Right, it's this thing, lambda of n, which is equal to lambda of pq. P times q, 2 primes, equal n. So this is the product of 2 primes. Now, what we found previously, using Fermat's little theorem, is that there exists an exponent to which we can raise our message. Our message being a number, so we can raise it to a certain power. We raise it to that power, and we take that value, the result of that exponentiation, we take it modulo some number. Why is that? Well, when we take an exponent modulo some number, eventually we are going to loop back and get the same number we started with over again. That's how RSA works. We take a message, we raise it to a power, we hold on to that. That's the secret. We raise it to a power again, and then we get back the original message. That's what Fermat's little theorem says. What this does is enable you to do that without your numbers growing too large. That encryptor is 5 decimal digits long. It is 16 bits long. It is 4 or 5 hex digits long. It's 5, just barely. That is a big number. The message here, say that message is the text hello world. Hello has 5 characters, world has 5 characters, and usually there's 3 punctuations in there, right? So that's about 13 characters. 13 characters by 8 bits is whatever 8 times 13 is, which is 104. So if I take a value that is the size of 2 to the 104th and raise it to the power of 2 to the 16th, I have a very, very big number, right? So to not deal with numbers that big, which would cause my computer to halt and burst into flames, right? I don't actually raise m to that power all at once. What I do instead is I square m. I know m is less than n because I just took it modulo n, right? So I square something and it is maybe twice as big in size as n. Now n is of size, would we agree? 4096 bits, right? So it's not going to be that big, right? It has some fixed finite size, right? And it could be quite large, but it's still fixed finite size. We square numbers of that size and they get up to twice as big in terms of bits, not in terms of values, right? And then we take the modulo again and they go back to being smaller in size. So what this enables me to do is work with much, much smaller numbers. And in fact, this caps the size of the numbers I'm working with. I no longer have to work with arbitrarily large numbers. And arbitrarily large numbers are arbitrarily slow to form calculations over. Many of you worked on big division this week, right? You may have had a sense that the bigger numbers you divide are much, much slower than smaller numbers, right? The speed of these division operators slows down exponentially in the size of the number, right? So, have you all taken algorithms? It's not required. Okay. I know some of you took algorithms. I think you should all take algorithms. You should all take algorithms, you should all take number theory, and you should all take linguistics, right? But I can't force you to do that. I probably can. I wonder if I can force you to do that. Maybe I'll go mad with power. Okay. Has anyone here ever gone mad with power? I think we've all been there, right?
Yeah.
Yeah. It's a rewarding experience. And you need so little power to go mad, right? That's what I noticed. So you should all run to be on your local library board. Okay. So I have my number, and my number represents a message, and I keep squaring that number. Now, whenever I square a number, I can do this operation with exponentiation, where now I don't have to exponentiate by as large of a value. This is going to be much easier to demonstrate because I'm going to run out of words here pretty quickly. I know that says Windows PowerShell. That's a clever ruse. I only use Linux. I only use Linux. Does anyone else only use Linux? I think we've all been there. Well, you use Nix, which is almost the same thing, right? It's like Linux for cool people, right?
You put the Windows inside of the Linux for when you need to emulate something on Windows.
Yes. Mm-hmm. This is actually, it may appear that I'm running a Windows device, but actually this is a Hyper-V supervisor running a Windows VM that is hosting a Linux VM, also running on the Hyper-V supervisor. So if you think it falsely appears to you like I'm using a Windows device, I assure you I'm not. I'm only using virtual machines. So 2 to the 4th is 16. 2 to the 5th is 32. What we can do is we can say, well, 2 to the 4th is one way to calculate 16, but we can simply square 2, which equals 4, and then we can simply square that value. And I don't know precedence here, but essentially what we're doing is this. Looks like it prioritizes leftmost. So we can decompose these large exponential values, such as, for example, 65537, and we can decompose that to do the exponentiation one squaring at a time. We can do the same thing with 2 to the 5th. That didn't work. Why didn't that work? Does anyone know how math works? Oh, no, because it's 2 times. Right? That's right. It's weird with odd numbers. What's 2 to the 6th? So that's 64. How do we get that back? That's... What do I do here? How does my algorithm work? Let's see. I square and I divide by 2, right? Oh, no. Oh, okay, so it should be 2 to the 3rd. Right? No, that's too big. Does anyone know what I should be typing here? Oh, that's right. No, it's not. Why did I use 2? 2s are hard. It's this times that? Oh, yeah, because we multiply. Right? There's multiplications in here. And really, I think it makes more sense to think of this as I'm really missing the ability to do this. I would like that operator. This would look much more clear. Is there a way to change that? Can I change what the infix operators are in Python easily? Any Python power users? Okay.
The operator, plus
Yeah.
X, you have to make it into an object, or make a class.
Oh, okay, I don't want to do all that stuff. Okay, so let's say we got 2 to the 9th, which is equal to 512. That is equivalent to 2 to the 4th times 2 squared? Nope. Do I do it like this? Yeah, there we go. Oh, okay, the parens are the problem. I don't know the precedence of my operators, right? Okay, so 2 to the 9th. What's going on here? Okay, so we take 2 to the 9th, we divide 9 by 2, and that gives us 4, right? And then we are going to square that value because we factored out 2 times 4 plus 1 equals 9. So we're multiplying by 2 to the 1.
That's odd.
Yes. And perhaps we should actually stylize it this way. Two to the 4th to the 2nd is equal to 2 to the 8th, and we multiply that times 2 to the 1th to get 2 to the 9th. We can do this with 2 to 11. And we just put a 5 here. And we can do this with 2 to the 10. And we're just going to get rid of the times 2 to the 1. That's all that's going on. This is preserving the idea that n to the xy equals n to the x times n to the y. And don't run that in Python because it doesn't make sense. Are we like basically okay with exponentiation? I don't have any intuitive sense for exponentiation at all. I just know how to write code that works.
I don't think that's.
Is this wrong?
I don't. That's wrong.
How wrong is it?
That should be x plus y. Yeah, it should be x plus y.
Yeah. Thank you. Yeah, no, that makes sense, right? It's this one.
Yeah.
Yeah. Okay.
Oh, yeah.
And then this is.
That is. Someone did that.
What?
Is that right?
Well, it's,
Maybe.
no, 'cause it's just n to the x
Should be n
to
to
the
the
y.
x to the y.
Okay. This one?
Roughly.
Okay. That seems fine, right? And we can verify that. Let's do 2 to the what's a good thing that is x times y? Let's do 3. No, that's too small. Let's do 6. And then we can do 2 to the 3 to the 2. And we have to do parens, right? That's too big, right? No, it's fine. Okay. Why is it? It's like right associative or something? What is the order of operations it's doing? Oh, it's resolving
the exponent first? Why is it doing this? Does anyone know how Python works?
I know the order of operations is usually left to right, but with exponentiation it's right to left because it's assuming you want 2 to the 3 squared rather than 2 to the 3rd.
Okay.
All squared. I don't know.
And that's just how it's used in practice or something? That's why people do it? Okay. Cool. Well, I learned something today. I don't know what it is. What problem is modular exponentiation supposed to solve? We don't want to work with things that are arbitrarily big. So we throw in a modulo after every operation that we know increases our size. Multiplication increases the size of our numbers, right? We have to add bits every time we multiply. And we get to take away bits every time we mod. So we add some bits and we take away bits. And we can do this every time because we are all of the mathematics that we are doing in RSA is relative to some modular value. So we just do everything relative to that modular value. That's all. And this dramatically reduces our workload. My impression was, I think the first time I implemented RSA, I didn't implement doing the modulo at every stage of the operation, and like the biggest thing I could encode was like 7 or something, right? Like it was ludicrously expensive to do that. And I used pretty small keys too. I suspect that you will be working with a big div that has roughly this implementation. I did not show you my big div explanation. It doesn't even fit on a slide. And I heard some of you got big div done, so I'm eager to see your code. And you have I think you can keep working on big div as long as you want, basically. And I implemented separate remainder and quotient operations, like so, because frequently I only want the quotient or only want the remainder. I'm going to start talking about Euclidean division, and it is different than other division, because division takes 2 numbers and returns 1 number, and Euclidean division does not do that. It takes 2 numbers and returns 2 numbers. This is very confusing, right? Plus takes 2 numbers and returns 1 number. Minus takes 2 numbers and returns 1 number. Times takes a new number and returns 1 number. Usually division takes 2 numbers and returns 1 number. Euclidean division does not do that. It's a rule breaker. It's got a chip on both shoulders. It's a rebel without a cause. It is. It did not fight for the empire in the siege of Dagobah. Okay, we're gonna quit while we're ahead on the Star Wars trivia. There was maybe something called the Outer Rim. There was a siege of Coruscant, right? At the beginning of episode 3? Yeah, okay. I'm big into sieges these days, right? I've been reading about preserved foods. Okay. Naive division is my favorite form of division because I'm naive and I go out of my way to preserve my sense of childlike wonder about the world. Can I hear it for childlike wonder? You don't have to actually hear. Okay, that was surprising. I didn't know that would kill. Okay. Naive division is the entry-level categorization. So if I were to like set out a clever trap with like maybe a fun Lego or a delicious donut in it to try and catch a 6-year-old and ask that 6-year-old what division is, that 6-year-old would describe this operation that is over 2 integers and returns a rational value, right? Pretty much every 6-year-old I've ever spoken to after I explained the number system always described division in exactly this way. It is uncommon for 6-year-olds to use type hints in their Python descriptions. But the other day I caught a 13-year-old, right, who used the term dividend, spelled incorrectly just like this, right, and also divisor. I think that 6-year-old had been listening to my song Long Division, streaming now on mega.nz. It got taken down on SoundCloud because it's illegal. Even though I should be protected by both fair use and educational licenses. SoundCloud, get it together. I'm a teacher. I can do whatever I want. There's no crimes I can commit. Python uses this little thing right here. I think that's often called a slash, right? Can I hear it for slasher films? Okay, that one wasn't popular, right? Fun fact, C also uses slash, but only when you're working with float types. Float types are neither the rationals nor the reals. They are some secret, mysterious third thing. They store values like 1.2, and floats have the precision problems that we saw with the height example. Integer division, this is what happens if you set up a clever trap and you put the TypeScript programming language under like a vine trap in a CS department, right? Because computer scientists love TypeScript, right? And so if you capture a computer scientist under duress, that computer scientist will give up that this is what they perceive division to be, right? Which is an operation over either the natural numbers or the integers. And they probably, when they say integers, they mean the integers modulo 2 to the 64th, right? This is quite common. The computer scientists forget that the numbers they're working with are finite, right? And so it has this type. We take something that is an int, and we determine that int by taking two other integers. In Python, we use double slash for this. I have never once voluntarily done a non-integer division in Python. I think it should be against the law. I got kicked out of a Python user group for saying that. That's not true, I made that up. And C just uses this standard division, integer division, for all of its int types, right? So you all know int division. What is 5 divided by 2? 2. It is exactly 2, right? Don't mess with me on this. I know what numbers are. They're not a social construct, right? Okay. So the problem with division, right, is that unless you're using integer division, you can take two integers, apply a division operator, and get back a non-integer. This is really, really annoying if you're a computer and you can only perceive integers, right? And by that I mean naive division, right? Once I restrict to integer division, I don't have that problem. But I can divide two different numbers by the same divisor and get the same number back, which means that this operation isn't reversible, right? So 5 divided by 2 and 4 divided by 2 have the same results, even though 5 and 4 are different numbers, I've heard, right? Legends tell of a difference between 5 and 4. How did I express that? There exists natural numbers such that there does not exist ways to multiply natural numbers together to get that natural number, right? It's kind of annoying. Euclidean division is the solution to this problem. How do we solve this problem? We simply return two different values. Now, some of you may be C language programmers and notice that there's no way to return two values from a C function, right? Have any of you noticed that? Yeah. That's called being cool and good, right? So a lot of people aren't used to that. This is the same way that, like, when I am talking to another human and they say something goofy, I can only have one clever retort, right? Because after the first clever retort, I have to wait to get called on again when they pass around the little pillow you hold so you can speak, right? So C is just like the conversation where you have to be holding the pillow to speak. Have we all been in conversations like that, or is that only something people do to me? Okay, right. So how do we solve this problem? Well, in C, you can simply provide the location of two integers, update the integers at that location, and that's the same thing as returning two types. In Python, you get to cheat. There's this little thing called tuples that is an aberration. It should not exist, right? I note on this slide that it says loud cheers here for things being impossible in C. Do you all want to cheer for that, or do we want to keep going? All right, let's keep going. Okay. Euclidean division is also called division with remainder. At some point in my life, my elementary school mathematics teachers just stopped talking about remainders. And I don't remember when it happened. I just know that at some point, every time I did a division, I was expected to report a remainder, and at some point I wasn't. So at some point, the software in my brain switched from Euclidean division to naive division. And that's fine. There's nothing wrong with that, right? I am accustomed to seeing div used to describe this. And I think the reason I'm used to seeing div to describe this is that a lot of the other ways of expressing division are taken. Forward slash is used usually for integer or naive division. Backslash is usually used for set minus, maybe some other operations. Percent is generally speaking used for mod or remainder. I just called mine div because I was used to seeing it called div in pseudocode. It is frustrating to me that over what I would say, the unsigned integers, there are 3 distinct things that are all called division, and I called them naive, integer, and Euclidean. And they don't have the same type. One of them returns a float, one of them returns an int, and one of them returns 2 ints. But Euclidean division is used a lot in cryptography, and so I am introducing that today and motivating it with this lengthy anecdote. This is Euclidean division. I have implemented it here in Python using a combination of an integer division and a modulo. I believe in Python, but not in C, x% y, if these things are both integers, that always returns a positive or 0 value. Is that correct?
Yeah.
Okay. So this takes 2 integers and returns an integer and a nat, or the naturals union 0, right? We're in the computer science class, so I don't have to specify 0. I want to introduce some terminology. I think I introduced minuend the other day, and everyone hated that because they thought it was minimum. My haters were attacking me. I was beset on all sides, but I fought them off. So I'm going to use, I think, these combination of terms. We divide a dividend by a divisor to get a quotient or a remainder. We can also refer to dividends as numerators and divisors as denominators. I usually think of these in terms of fractions or ratios, and I think of these in terms of arithmetic operations, but logically there's no difference, right? Quotients, fractions, and ratios are all the same thing. And then remainder is modulo if the dividend and the divisor are naturals, so if they are positive. And I am using natural and unsigned integer, and the numbers 0 and larger all the same, all interchangeably. Euclidean division preserves the following equality, which is of great use to us, which is that the divisor, the thing by which we divide, and the first output of the tuple, the quotient, the divisor times the quotient plus the remainder equals to the dividend, the thing that we divided. We divide the dividend by the divisor and get back a quotient and a remainder, and this is the relationship between them. It is defined relative to multiplication and an addition. The remainder is restricted to the naturals, and the remainder must also be smaller than the divisor, because if we can divide this thing, the remainder, by the divisor, then what we should do is we should add 1 to the quotient. So this quotient is the largest value that satisfies this inequality for any divisor and remainder. The quotient is the largest number, the remainder is the smallest positive value. Remainders are small and positive. This is good for us because we're about to use remainders a lot. When we are using Euclidean division, we get to stick with the integers, and we also get to have absolute precision. We're never going to divide 2 similar numbers and get the same result, so we're never going to lose information. And Euclidean division is well suited for use with the unsigned integers, and in fact with the unsigned ints, right, because we can use it to do modular operations. Does that all make sense? Does it make sense why I want to have something that's reversible if I'm trying to do cryptography, and that works with integers if I'm trying to do cryptography, right? This is a fundamentally annoying problem I need to solve. So that's Euclidean division. A lot of you have probably heard of the Euclidean algorithm, which is the algorithm with no m. Why is there no m yet? Because we haven't finished fig RSA, so we can't generate m's, okay? It is an algorithm with algorithm in the name. This is super cool. Sorry, I'm going to keep ranting. How's everyone doing today? I love this part of the semester because I feel like the fatigue has really set in, and that's inhibited my ability to not feel joy, right? So I'm only feeling joy, right? Does anyone, can I hear it? No, I'm not going to keep making you cheer. That's too much work for me. Okay. Salem, are you ready to rock? Okay. I was talking to the MSCS students, right? And one of them was like, you know what would be so cool? I was like, yeah, what would be so cool? And it was like, You should teach data structures and algorithms in a systems programming language. And at that point, I had to make my elaborate reveal that this is actually data structures and algorithms in a systems programming language. I'm just pretending it's about cryptography to trick you, right? And you may have noticed this because I taught you previously something that had algorithm in the name. It was the secure hash algorithm. So I am teaching you algorithms. I am teaching you different algorithms than which you would normally be taught in an algorithms class, such as some of you took algorithms. I'm going to list off some things and see if you did them. Did we do min, cut, max flow? No? Okay. Did we do traveling sales? Okay, one of you nodded and one of you said no. Name one algorithm you did in that class?
Depth first search, breadth first search.
Oh, the graph algorithm.
Star.
Dijkstra?
Yeah.
Okay, Dijkstra, cool. Graph theory is cool and fun, right? You know what else is cool and fun? The secure hash algorithm has algorithm in the name. I noticed that breadth first search does not contain algorithm in the name. Can I get my fact checkers on that? Did anyone see the term algorithm in the name of breadth first search, right? So it seems like the secure hash algorithm is more of an algorithm than breadth first search, right? Which means that secretly this whole time I have been the algorithms instructor, right?
What's the algorithm in your name?
Well, it's not in my name. I'm the instructor, right? Do you think I should legally change my name to Calvin's algorithm?
It could be your middle name.
You don't know my middle name. Maybe it's already algorithm.
I don't think it is.
No, it's Kennedy. No relation. To my knowledge, I'm not American royalty. But if you want to vote for me, that would be cool. My platform is C89. Okay. So the extended Euclidean algorithm, or the extended GCD algorithm as it is sometimes called, also has algorithm in the name, which I am humbly submitting as evidence that this class should be eligible for algorithms credit more prominently at the master's level. And then the data structures portion comes after break. In systems programming language, I think you do the algorithms first and then the data structures second. Historically, you do data structures and algorithms at the same time because you use the data structures to do the algorithms, right? So we're kind of doing that same thing. Euclid's algorithm is named after a Greek scholar preserved by Islamic scholars, and I guess that presumably Arabic is the name of the Islamic Golden Age Egyptian scholar that wrote down the version of Euclid's algorithm that has been preserved. I try to do my part to give people their flowers, and a lot of the people I give flowers to are people that lived in Egypt 1,000 years ago and took notes in class. Can I hear it for taking notes in class? Yeah? Anyone taking notes today? I never took notes. That's why I'm the way I am. If you take notes in this class, you should send them to me at the end of the term so I know what I taught. Because I'm living in the moment. I don't form memories. In that way, I'm like in a memory unsafe C program. Okay, sorry, moving on. Okay, so given two values, the extended Euclidean, well, not extended, the Euclidean algorithm finds the greatest common denominator. How does it do that? Subtraction. To the best of my knowledge, this algorithm is the algorithm that invented division. It defines division using other operations, namely subtraction. What does it look like? We're going to take A equals 1071 and B equals 462, and we're going to find their greatest common denominator. Does anyone see what it is offhand?
At least 3.
It is at least 3. Good work. Do you think it's 3 and one other prime that are multiplied by each other? I think it's 21, but that's because I remember. So the first thing I'm going to do is that Python, it's great, right? There's no possible way you could express this in another language. Certainly you couldn't simply write a macro that does this, right, in C. There's no way you could do this in a single line macro, so don't even try. And if you do try, let me know how you did it. So we're going to put the maximum value first, and we're going to put the minimal value second, right? Why are we going to do that? Well, we've talked a little bit about doing things with maximum and minimum operations in Euclidean division, and that's what we're going to do. We subtract the smaller value from the larger value until it is no longer the larger value. This is division by repeated subtraction, right? But this is not actually classical division. What we're actually doing here is we're calculating only the remainder, right? So if I divide 21 by 4, I subtract 4 from 21 some number of times, and I'm left with a 1, right? Shout out 21. 21 pilots? Okay. They did heathens, right? Yeah. We can keep doing this over and over again. And if we keep doing this over and over again, eventually the smaller of the two values will be 0, because we will divide by the greatest common denominator, which could be 1, right? So we could get down to y equals 1. This is the loop, and I just put an exit in here because I didn't know how to express the idea of this being a terminating loop in a single line in pseudocode, right? Let's look at this all put together. This is the Euclidean algorithm, which I cannot spell. Every single one of these slides, I manually tried to spell it the first time. This is what I got the first time. That says, as you can see, Euclidean algorithm. It takes 2 integers and returns an integer. What does that integer represent? That integer represents the greatest common denominator. Well, the minimum of a and b is not equal to 0. We take a and b and we assign it to the max and min, so we put them in order. Then, while a is greater than b, we subtract b from a. And then we return the maximum value at the end when the minimum value is 0. Easy peasy. Should we run this? Who loves code? Oh, that worked. Okay. Wow, crazy. What are some numbers that we love? There you go. Anyone have 2 favorite large numbers that they know share a non-1 common denominator? That's kind of cool. I don't know. So anyways, this is, wait, what's the precedence on that? Why can I not type? Should we do monkey type again?
No.
What is that?
That was a pretty large number. Let's try smaller ones. That's pretty fast. How big can we go? That's fine. Okay, so that's the greatest common denominator. This is basically the exact same thing that was written in that generative AI. The only difference is we use subtraction, right? So let's update this over time. Essentially what we're doing here in these lines is we're just performing modulo with repeated subtraction, right? So we can displace that and just write a modulo, right? I think this is the only time I've ever written mod equals, that's kind of cool. I don't write that very often. And one of the reasons that I think this algorithm is defined without the use of modulo in it is that this is the algorithm that, to my mind, defines what division is, so it's weird to use division inside the algorithm. That would be a recursive definition. Nothing wrong with that, but can be a bit confusing, right? Because to understand recursion, you must first understand what? Recursion. Ah, okay. Yes. I thought this was way easier to understand recursively, so I wrote something called recmod, which I thought was a cool name. Isn't that a cool name? I don't know. Recmod. And you'll see this is recursively defined. Take a minus b if a minus b is greater than 0, otherwise a. I think it's a little bit nicer if you split out all of the maxes and mins into a helper function that reorganizes things. I don't know. This code all works. Probably. Does it? I don't know if it works. I did write this code and test it. 21 and 18, right? Cool. My impression, Professor Lucas Cordova every once in a while says to me, Calvin, it's okay to teach your students that they can write more than 1 line of Python at a time. And I respectfully disagree, but I would like to state emphatically and for the record that I went out of my way to write 2 lines here when you only need a 1-line solution, right? So if you are talking to the other faculty members, I want to hear that my code is self-documenting. That's what I want to hear them say. I want them to say, Calvin, all of the students were talking about how your code is self-documenting. That's what I want to hear, okay? That we can all understand that? Okay. It's self-documenting. I much prefer, right? Okay. One of the other forms of feedback I get is, why do you exclusively write your code in lambdas, right? Some of you perhaps like the def keyword. So I wrote this with a definition. And I also added type hints, because if you're going to use defs, you get to use type hints. I don't make the rules, right? If you don't want to write your type hints, you have to write a lambda expression. And so this is the same idea. I define an inner function that does all of the recursive operations, and an outer setup that puts A and B in order. And then it recurses, and it just returns everything. Does this code relatively make sense to us? We can see that this is the same thing we worked with earlier. We just have an inner function. This can get quite simple if we remove type hints and just trust that A is bigger. Just real quick recursive statement. And as we see, GCD calculation is not that painful, right? This is not too bad. We can demonstrate this, and I added a print statement to demonstrate this. Let's go ahead and run this. Do you all believe me it's going to do that? 1071 and 462. EA. EA stands for effective altruism. I don't know. I think this is kind of cool, right? So we take 1071 and we divide it by 462, and we're trying to find the greatest common denominator, right? So what do? We take 1071 and we repeatedly subtract 462 from it, right? We get 147. So then we repeatedly subtract 147 from 462. We get 21, right? And we find that this thing is divisible by 21, right? What this is essentially doing is dividing by progressively smaller numbers until we get to something that is the common denominator, right? I just think that's aggressively cool, and I hope that makes sense to you. Both of these things are divisible by 21, and that is, in fact, what GitHub Copilot wrote. So GitHub Copilot did not cite either Euclid or Egyptian mathematicians, and is therefore plagiarizing and should be put in jail. But we're prison abolitionists, so we don't believe in that. This is how to visualize the algorithm. It's often visualized geometrically, so this is 1071 on this side, and it is 462 on this side, and I think that is pixels, right? This is a roughly 1920 by 1080 screen, probably? That seems fine, right? This is probably not 1071 vertically, right? Because otherwise it would be the entire screen. Well, it's pretty close. And what do? We first take out the big 462s, then we take out 147s, and then we calculate, then we take out some 21s, right? So here we're taking out the 147s, and then we're taking out the 21s. I think a lot of the early arithmetic was done geometrically. I don't know if that's true. Does anyone know the history of math? Okay. Well, you should tell Professor Erin McNicholas to teach her a history of math class. Okay.
They didn't have variables or like writing out. They would just geometrically describe everything.
Is that true?
That is true. It's in the McNicholas's number theory textbook.
If it's in the McNicholas's number theory textbook, it is the truth. I'm reordering things. What am I doing? I'm changing the order of the extended Euclidean algorithm and Jeff Bezos' secret identity, which is he is the Batman. A lot of people don't know that. It's true. What do we think about Batman? Is Batman like a fascist fantasy, or is it like a liberatory thought experiment, right? These are the questions we should be asking. Do we want to be freed by the Ubermensch? I don't know. I don't, but maybe you do. Is Batman cool? Okay. We also computed the multiplicative modular inverse. This is bad and slow and wrong. Don't do this. This is banned. This is banned. You're allowed to do this with the 64-bit. This is how many times you would have to run your loop. Let's just take a look at this real quick. Look at all these numbers. Do you know how much Monster Hunter Wilds you could play on your computer instead of doing this division? Probably like 26 hours. Look, it's still going. Look at this. Oh, my favorite number's in here. Do you see it? It's 7. It's right over here. Okay. Oh my gosh, it appeared again. Still going. It's still, do you think we're almost to the end? Don't look at the scroll bar. That's a spoiler, right? It's more fun if we don't know. I thought about animating this. Okay. In the extended, or in the, I keep saying extended. They're conceptually linked in my mind. In the Euclidean algorithm, we only find the greatest common denominator. But we're throwing out a large amount of information. And specifically, the information we're throwing out is all of the divisors, or rather the quotients, right? We are only keeping track of remainders or mods. We are not keeping track of quotients, but we can keep track of quotients. And if we keep track of quotients, we will know what we can multiply the GCD by to get back to the original big numbers. Why is that useful to us? Well, we can use this to compute multiplicative modular inverses. How? The GCD of two co-prime numbers is 1. And now we're going to know what we have to multiply 1 by to get to some number in a modular base. So we can synthesize multiplicative modular inverse relative to some n out of the Euclidean algorithm. How are we going to do that? So I think Jeff Bezos is named after a 1700s French scholar, but I think this result is a derivative of a 300 AD or perhaps CE or perhaps BCE Chinese result. Please note on the course of Alice that I am incorporating diverse voices in this class. I am very annoyed with Europe. Is anyone a pan-European in here? Can I hear it for the European Union? Kind of like that? Yeah, very interesting supranational project, right? Maybe it'll work. Seems like it was reliant on United States defensive guarantees, I'll say that. Okay. But enough about me. Let's talk about Bezos' identity. For all a and b elements of the integers, there exists in x and y elements of the integers such that a times x plus b times y equals the GCD of a times b. The GCD is a linear combination of the multiples of the GCD. That's not too surprising, right? What this really just means is we can factor the GCD out of any of this stuff. This is also a way of expressing the multiples of a GCD. Why is that? Any two numbers which share a GCD are multiples of that GCD, right? 21 and 18 share the GCD of 3. One of them is 7 times 3, one of them is 6 times 3. Not that complicated. Okay, how are we going to use this? We're going to recall that the message to the encryptor to the power of the decryptor equals the message when we are is equivalent to the message modulo n, where n is some special value chosen to preserve this equality. We need to figure out what d is. We've already set e. We have already computed n. And we do not get to decide m, right? So we take these as given, and then we compute n and d that satisfy this equivalence relation. I have a question. I have a Willamette alum in the grad program that is taking this class that seems to have a preference for referring to this operator as congruence instead of equivalence. Do we prefer that?
Yes.
Okay, so so when I looked into it, I found that equivalence is a superset of congruence, right? So congruent is an equivalence relationship. Should I say congruent for the rest of the term?
Yeah.
You don't care.
I mean,
I don't care now. Modular congruence is technically the name of the equivalence.
but there's another thing going on here that involves modular. Yes.
What if I call it conquivalence?
I don't like that. Don't do that.
I think we can give equivalence and congruence a couple name, and it's conquivalence. So the following are conquivalent. We need some d that is the multiplicative inverse of e, of this thing, mod the totient, Carmichael's totient, which is the LCM of 1 less than each prime, which is this thing. So we're trying to find d. And this n is helpfully already an LCM, right? So we're going to get some special features there. We need it to be the case that E times something equals 1. E times something equals 1. That is a linear combination. E and the lambda are co-prime by construction, right? Because E is prime, so it is co-prime with everything. And we simply make sure that this is not a multiple of E. And since this thing is not a multiple of E, which we can check and make sure, their GCD is 1. So that means that E times X plus lambda N times Y equals 1. Now, we're doing one other secret, hidden, super cool, fun thing that everybody loves here, which is we're doing all of these operations modulo lambda then, which means this thing is conquivalent to 0, which means we don't have to deal with this term at all. This term is banned. This term does not pass go and does not collect $200 because this term did not vote for socialists in its local elections and doesn't have access to universal basic income. I feel like you're falling asleep. That one was pretty funny. Okay, so what do we have here? For all E, 65537, I don't know why I say for all, but we are restricted to be co-prime here. And lambda of n, which is the LCM of p minus 1, q minus 1, there exists some x such that E times x is conquivalent to 1 mod the totient. That is just, I don't know. To me, it seemed like non-intuitive, but then you look at every one of the steps and you're like, oh, that's trivial. It's like 6 trivial steps resulting in something that seems completely esoteric. I always heard this called the extended Euclidean algorithm. It looks like the terminology extended GCD algorithm is catching on. Number theorists, what did you call it in your class?
Extended Euclidean algorithm.
All right, I'll talk to Professor McNicholas and figure out what I'm supposed to be saying. Does it say extended Euclidean in the textbook?
Yes.
Okay. We'll take that as ground truth then. But it does look like, I noticed when I was doing my research, I've seen people refer to this as the extended GCD algorithm. It is also possible those are different algorithms.
I've seen them referred to the same thing before.
But also, like, this is a lot of words, right? Extended greatest common denominator algorithm? What is this, an algorithms class? We don't have time to say that. Yeah, so my recommendation is if you're Googling this, call this the extended Euclidean algorithm. And if you're trying to keep with what I expect to be the ongoing trend in naming things after what they are instead of after people, I expect it to be called the extended GCD algorithm in the future. All right, and that's Bezos' identity. We still have the bad MMI. We haven't fixed that yet, but we're going to fix it right now. Whenever I see a meme about, like, I could fix him, it is about fixing this using the extended Euclidean algorithm, right? I'm going to call this thing EEA, which is effective altruism, right? It is the same as the effective altruism.
Like extremely effective or something?
It's the version of effective altruism that is effective. Here, so, right, there's effective. Well, I think perhaps actually we should think of them as functions, right? So we have effective, which we apply to altruism, right? And so I think there's two ways to think of this. I think of it as being effective applied to altruism, right? But we could also think of this as perhaps a map over effective, I don't know. The extended Euclidean algorithm, or the extended GCD algorithm, was not super easy to implement, so I'm going to show you essentially 15 different slides that implemented in different ways, some of which helped me understand it, some of which didn't. This is the rare case. I looked at the pseudocode to this thing on Wikipedia, and it turns out I did not understand it, which I did not know, because I got the code to work, right? But I didn't get my brain to work. And I'm unused to doing that. It is very unusual for me to be able to get code to work without understanding it. But I was able to do that with the extended Euclidean algorithm. It's just arithmetic. It's a little bit too easy to get it to work without understanding it. The reason I did not understand it is I had always seen this thing written iteratively, And I don't think iteratively, I think recursively. I only have a recursive stack in my brain. I don't have any loops, right? So I'm going to show you a combination of different ways to express this idea. And I got them all as consistent as possible, but there's just some overhead that's like hard to keep track of. I am regarding the Wikipedia simplified pseudocode as ground thrust. That's supposed to be truth. What was I thinking? I was probably playing Dragoon in Final Fantasy Online 14, A Realm Reborn. And we're going to call this extended GCD. I did like that name. This is the Wikipedia pseudocode. Have you all seen pseudocode like this before? Is this relatively familiar to us? So some things that are nice, not using single equals assignment, which should not happen in any programming language. I don't know why that's been convention, right? They just slammed a not equals in here. That's a little cursed. I didn't know that was allowed. Right, that's not an ASCII character. That's not in UTF-8.
That's what it looks like on my machine.
That's what it looks like on your machine?
Yeah, with the pictures.
You have that key on your keyboard?
No, but with it.
What kind of computer do you use?
It's the font, like different font.
Yeah.
It's sharing.
Everyone has a Mac, easily type that character.
I've never heard of Mac. What is that? Is that like something that is that like a sandwich at McDonald's? Is Mac named after the Scottish prefix for a last name meaning son of?
It's a type of apple.
Ah, like a Macintosh Apple?
Well, yeah, it's just short for that.
Okay, I see. Here's a dual while loop. Just kidding, that's actually a regular while loop. We calculate a quotient. Remember, when we were doing the Euclidean algorithm, we were using quotients a lot, right? This is using repeated subtraction. This was super non-obvious to me. I had no idea what these lines of code were doing when I first looked at this. This is just computing mods. Do we see that? This is multiple assignment. We are setting r equal to old r minus quotient times r. That is the mod. If we divide old r by quotient times r. That's mad goofy. We'll look at this recursively. There are two Bezos identities, or the Bezos coefficients, which are computed here. This is already a simplified form. Usually there's R, S, and T, which is computing both of the coefficients separately. You only need one of them because you can do this modular activity at the end. This is following the pseudocode, convention of just saying output instead of having return. We do not need this because we do not need both of Bezos identities. Let's go back a gazillion lines. Remember this thing? We didn't care about this because it turned into 0 in our modular system. Remember? These slides. This thing tends to 0 because it is some value times lambda n, and we are taking it mod lambda n, so that's going to 0, which means we only need x. We do not need x and y. We only need x. We do not need x and y. The extended algorithm is going to produce x and y. We modify the algorithm to only return 1, so we throw this out, as we do here. We do not keep y. So that simplifies it as follows, and this is starting to fit on one screen. Okay. This implementation does not use modulo, the pseudocode implementation, but this is equivalent to saying mod here. I didn't know the best way to do this in pseudocode, so I just wrote mod. Does that seem okay? Do you sometimes write mod to express this? What do you do in LaTeX? Is it slash mod? Has anyone ever written this before? Slash mod? Okay, cool. Anyways, these things are the same. Old r mod quotient is the same as old r minus quotient times r, right? And that's because old r is divided by quotient, okay? So I changed these over to mods because we don't want to do repeated subtraction, right? Okay. So we put all this together, and we're starting to get something that is a little more comprehensible and something we can start to write in Python. I got ludicrously confused by this multiple assignment, old r. Presumably this means new r, right? How do you decide which one's old? What does that mean? Well, the reason for that is that this is the iterative implementation of a recursive algorithm, and we don't ever actually historically hold on to the old values, right? They just persist in the calling convention. And so I think we are able to get rid of them by converting this over to recursion. So I recursed. And this got rid of all of the old S and new S things, right? And what we have here instead is we are loading A and B in the extended GCD, which we call here. And we are loading those with R, S, and T values, right? So we're just changing the order of R, S, and T, R, T, and S, right? R is the remainder, which is going to become the GCD, and then S and T are the two Bezos constants that we are computing over time. And what we're doing is this is an update. This is new T, and this is old T. We put old T inside at where S is going to be, and so on. This looks confusing, right? Yeah, carry on, don't worry. We can get this to run in Python. And from here we can do extended GCD. What do we do? 1071 and 462, is that right? And what does this give us? This gives us the Bezos constants, which are the values we multiply by these values to get that value. You don't believe me, that's okay, I can demonstrate it. 7 times 462. And that's 21. So, that's cool. I think that's cool. I don't know if that's cool. All right. What else can we put in here? We did 21 and 18. That's slightly easier to think about. 21 times 1 minus, no, plus negative 1 times 18. Oh, it's 3, right? And then if we put in co-prime values, 21 times 1 plus negative 1 times 20. Oh, it's like the multiplicative inverse. I don't know. That seems fine. Okay. Here's an example. That's what I just showed. So I was about here implementing my big RSA when I remembered that in 4096T, I assumed all of the numbers would be positive. Did any of you do this? I did this. I did not implement T's complement. I was like, that sounds like real work. So good luck with that. What I started doing is I started separately tracking a sign bit, and I wrote my own custom subtraction function that had multiple return values returning the sign of the result and the magnitude of the result. Do we say magnitude, the absolute value, the size of the value? And I got that to work. But anyways, here is how we find D. The only thing I do here is I make sure that D, which is the result of the extended Euclidean algorithm, I keep adding the modular base to it until it becomes positive. Why am I ad blocking my own website? Why don't I have sponsors?
I feel like you talked about this.
Oh, what did I conclude?
That was for the
VPN?
It was for the VPN sponsor. That was different.
Oh.
On the website.
Yeah, no, that's... I don't think this is like a real thing. I don't know. They wire transferred me $300. This is not the one that I worked with. No, this is Ace Aurora. It didn't have an English language website. Anyways.
I don't think this is a real thing. You didn't give me $300.
I got a mug in the mail that had the logo on it. Maybe I'll send you all the video. I put it on mega.nz, the website for cybercrime, right? Because I was doing cybercrime. And that's the extended Euclidean algorithm. Any questions? I'm going to put in my journal tonight that I explained this so well it had no questions, and I'm going to put a little heart next to it and write, "Good job, Calvin." That's what I'm going to do.
They use XOR check bars. It's two numbers in the same XOR.
Why don't you just XOR?
You
Use
can't.
XOR instead
There's
of
no way.
There's
There's,
both.
yeah, XOR's got to be way faster than subtraction. You don't have to maintain carries.
Yeah.
So I thought it would have been fun, and I didn't do this, right? What if I made you all implement addition using only the bitwise ops? So like instead of having to make division out of plus and minus, right, you have to make it out of bitwise ops.
Use XOR. Then you do.
But you see, you have to think about this for a while, right? Because it's not as easy as we think. Is it?
You do XOR, and then I think it's and for the.
5?
Well, Jimmy,
It's
shouldn't it
and
all just,
XOR, and then you just and XOR.
shouldn't it all just be NANDs?
Is it this
I
one?
mean, if you want to implement XOR and it using NAND, you can do that, then use those.
What's the typo?
But under the
Ben, you want to?
There's fast.
1 second, sorry, I'm still digesting the slides.
Anything goes this week. Oh, to this. Yeah, I'm going to say I did that on purpose because I was trying to be fast. Okay.
And right now, I'm working. I thought I could finish a virtual machine in one and a half